All right, I'm Andrew Bennett, and these are my associates.
Robert Ham?
Jacob Kelly.
Yes. And we'll be talking about the forms of chemical corrosion today. First off is ammonia. Ammonia is a compound of hydrogen and nitrogen and is found pretty much everywhere because hydrogen and nitrogen are both required for living things, which means just about every living thing has them in one form or another. Ammonia is a basic element. It is not acidic, but it is used as a neutralizer and a cleaning agent in a lot of things. So you'll often find it in a lot of household chemicals and cleaning agents. Yeah. And this is a the type of corrosion that ammonia specifically causes, or that's the topic of this presentation, is ammonia stress corrosion cracking. The typical environment for this is usually in brass, specifically copper. Copper is very susceptible to ammonia, and so brass is where you usually find it because that's used for a lot of piping and industrial work, but copper in general is pretty weak. So you'll typically see it in brass tubes in cooling water services like here, in a lot of factories. The reason why it's found in a lot of water cooling especially is because often they will use ammonia as a kind of neutralizing agent in water to clean it and stuff, and so it'll react with the brass tubes lots of times. Corrosion can also occur in ammonia storage tanks. As I mentioned earlier, copper is particularly susceptible to ammonia stress corrosion cracking. Steel is resistant to aqueous ammonia, but it is very vulnerable to anhydrous ammonia. The possible vulnerabilities of ammonia is really any ammonia in contact with copper structures is bad. There's not, you can alloy it with certain things, but really the biggest vulnerability is just if it's in contact with copper, then it's probably going to be vulnerable. Though a good way to prevent it from corroding steel structures with anhydrous ammonia is by adding some water to it. Even just a level as low as 0.2 will be good enough to kind of prevent it. Ammonia affecting factors. Ammonia is caused, as I said earlier, it's found in a lot of things. And so living bacteria will often cause it in brass pipes and things like that. Neutralizing and cleaning agents, like I mentioned, also contain a lot of ammonia, so that will cause it. And ammonia is detected in brass pipes, it will be vulnerable. Here's the corrosion cell mechanism. This is a diagram I designed myself. Stress corrosion cracking, as I've already mentioned. Ammonia usually reacts with the copper in elements like that, forming cuprammonium, and that's usually what causes the weakening, which enables the stress corrosion cracking to take place. Ammonia stress corrosion cracking usually just takes the form of deep cracks in the surface, deep brittle cracks. If left unchecked, the structure can completely fracture, but that's usually only in severe cases. It takes a while for it to get to that point. Fun fact, they originally discovered ammonia stress corrosion cracking. It was originally called season cracking, or that's still kind of a form of it today, but that's how they initially figured it out. And they actually, when the British Empire controlled India, then a lot of the soldiers would report that their cartridges, the brass cartridges that they stored there, were malfunctioning, they were cracking and things things like that. And so what they had done is over the winter during during the rainy season, they had stored their cartridges in stables. Now, does anyone know why that might be a problem?
What bullets aren't good?
Huh?
What bullets aren't good?
Maybe urine? Maybe urine.
Yeah.
Stables?
Yeah, the answer is that they stored it in the stables, and urine contains a lot of ammonia. And so the horse urine ended up getting on all the cartridges, and that made them crack. So the way they solved that is by annealing the cartridges after they had made them, so there was no longer like residual stresses for the ammonia to take as much advantage of. Here are the standards for ammonia. The ASME standard, or ASME standards, describe testing methods to determine stresses in copper. You can also use a vapor test to determine the severity of the threat. This is actually a rare picture of it, and I managed to actually get the standards off of a Russian file sharing website, so I hope you appreciate the risk that I took.
+5 right there.
So,
That's why we're doing the World Cup.
so anyways, how to test for ammonia in brass pipes. Eddy current testing is usually the best thing you can do. Here's a picture of it. You've got a little meter and you hook it up to the pipe, and it'll give you a reading. The other thing for steel surfaces, magnetic particle testing is more effective. And this guy's doing it right there. So, how to control ammonia is, like I mentioned earlier, bacteria can cause a lot of ammonia buildup, so do everything you can to keep the pipes clear of bacteria. Avoid using ammonia in coppers unless they have proper alloys, which I think I'll be getting to in a second. In steel structures, like I said earlier, the water level of just 0.2% water will prevent the corrosion in steel. So here is the second type of ammonium bisulfide corrosion. Well, it's a different type of corrosion, but ammonium bisulfide. Typically, ammonium bisulfide forms the basis for sour water, and the place where you'll see a lot of this is typically in like hydro processors and water treatment and refineries. And the reason for this is because sour water can just be extremely corrosive in the wrong environment. Carbon steel is very, very vulnerable for ammonium bisulfide corrosion, and it's usually the place where you'll find a lot of the most severe damage. So if you're going to like have water processors and things that might interact with sour water, then you need to have it be alloyed with like stainless steel and other types of things. Possible vulnerabilities towards ammonium bisulfide. U-bend tube design in hydroprocessors and air cooling systems are often vulnerable because of the velocity. In U-bend tube designs, when the water rushes around, typically it can hit the curve of it really hard, and velocity can really affect the severity of ammonium bisulfide. So avoid that if possible. Like I said earlier, carbon steel should not be used. They should be alloyed. Affecting factors, ammonium bisulfide concentrations of 2% or more create corrosive environments. So if you can keep it under 2%, then the risk of ammonium bisulfide corrosion will be much less. High velocity, like I said, increases the risk exponentially. Here's another custom-made diagram showing just how ammonium bisulfide forms. It forms it is a salt derived from an ammonium cation, that's ammonia, and hydrosulfide anion. And so those two form together to make a salt. The most frequent type of corrosion that you see from ammonium bisulfide is hydrogen blistering. And this is kind of an appearance of it. It can look real nasty. Yeah, so it's mostly cracking and blistering. It frequently does general type of corrosion. It can spread out in a large area, but where you'll find it especially concentrated is in high velocity areas like in the U-bend tubes and things like that. Here are some more standards. The NACE standards, the one that I found, summarized the result of a study done over ammonium bisulfide corrosion. It focused on refineries and water processors and things like that, which is usually what this one is overhead water strippers. This I didn't get off any sort of site, it was just off the internet. It's from the NACE Expo, so they did a little expose on it. How you test for ammonium bisulfide is you typically analyze samples of sour water to determine its concentration of ammonium bisulfide. And as I mentioned earlier, if it's under 2%, then that's manageable. There's a specific software tool called Predict-SW that was developed to quantify and predict threats to sour water systems by analyzing the various little chemicals and concentrations in there. How you can control ammonium bisulfide. Some important alloys that you'll see with steel to help prevent it is titanium, aluminum, and nickel. So if you're using it in a refinery style setting where you're coming in contact with sour water, that's what you want to use. Low concentrations will do it. That'll prevent it from happening in a lot of cases. And you should try to always lower the flow. Yeah, so that's it. My part.
Thank you. All right. Appreciate it.
That's too close.
That's two. All right. This is fine right here.
Perfect.
Second one. Carbon dioxide. This form of corrosion is only corrosive to metals when it happens to be dissolved in water. When it is in water, dissolved as, well, it's dissolved as three different things. Bicarbonate ions, carbonic acid, and carbonate ions. The difference being bicarbonate ions having simply an H atom, hydrogen atom, and the carbonate ions having just CO3, which is just an additional oxygen. Typical environment you find it, like I said, it's found, it's only corrosive when it's in a liquid environment. So it can be found in rainwater. That accounts for acid rain to some extent, but I Googled it and looked it up and it's not that much. It's like, I don't remember exact numbers, but it's not really acidic to any horrible degree. The majority of corrosion encountered due to CO2 is in the oil and gas production industry because of those hydrocarbons that were mentioned in previous presentations. They wreak havoc on all types of metal, especially like H2S, hydrogen sulfide. It has a whole lot of terribleness going on in it when it gets into contact with the metal, and terribleness being electron exchange and therefore corrosion, completion of a mechanical cell, or the mechanical representation of a corrosion cell. Susceptible materials. Any metal in contact with CO2 in the water as bicarbonate or carbonate ions will be vulnerable to attack depending on the levels present in the water, which that is to say pH essentially in a way. Even steel, although highly resistant, can be attacked via breakdown of their oxidation barrier as described earlier in other presentation, especially in the instance of water or liquid flowing from high to low pressure. That's called the seltzer effect, and that's basically the same thing as carbonated beverages like Coke. When you pop the tap, it goes from high to low pressure, and then all of that saturated carbon inside of the liquid is forced out into gas form due to the change in pressure, due to PV equals nRT. I think it's a formula. Yeah, The seltzer effect. When a liquid petroleum water being pumped undergoes a sudden change from high to low pressure, it is supersaturated with CO2, similar to carbonated beverages. Obviously, the increased concentration of carbonic acid results in increased corrosion rates. They share a positive correlation on that front. Affecting factors, temperature, velocity, and pressure are going to come up a lot when I'm going over the affecting factors for all of mine, because it's just the environment. It's how it affects what's going to happen. The higher the level of temperature of the fluid transported, the higher the corrosion rate of the pipeline. That also shares a positive correlation. Velocity, as with temperature, there's a positive correlation between velocity and corrosion rate, therefore higher. Pressure also retains a positive correlation between pressure and corrosion rate. So basically, you want to transport your liquids that are going to have CO2 in them, eventually bicarbonates. You're going to want to transport them at the lowest possible temperature, at the lowest possible velocity, at a very manageable pressure for an ideal corrosion prevention from that particular type of corrosion. The carbonate ions, this is the actual mechanism. Carbonate ions combine with the iron ions to yield iron carbonate, FeCO3, or the corrosion product, as evidenced here, leading to pitting. Well, not pitting, it's like the opposite of pitting. I'm not exactly sure how to describe that besides a buildup of corrosion product. This is just a picture to further illustrate how this is happening. They went over already how the electrons are being passed back and forth between this, with the carbon dioxide and the water being the oxygen that they had described. Kind of switch the roles, and that's what it does. This is what it looks like. I wanted to really get a good coverage of that scale that forms on it. It's also known as sweet corrosion. CO2 corrosion manifests as thick, brittle scale along affected areas of material. This leads to pitting, undercutting, and many other worsening factors. The standards that concern this are ASME 313. Chemical plant, petroleum refinery piping is typically the standard reference when sweet corrosion is expected, since that industry is at most risk for such an attack. If you wanted to test for this without being able to look at it, because it's obviously taking place on the inside of pipelines, you're going to have to take average pipe wall thickness readings externally, which are the primary step in monitoring any pipeline corrosion rate, and especially those expected to be exposed to carbonic acid. Ultrasonic testing methods are also, they are the most commonly used to determine this information rather quickly and efficiently. New methods of BWT monitoring, pipe wall thickness monitoring, are continually being developed. So just whatever new model is out is going to be as effective as possible, I guess. I don't understand. Chemical inhibitors are a method of controlling carbon dioxide corrosion. They can be added to the product to passivate the carbonate ions within. That I've found the most stuff about, honestly. I didn't cite every single source as I found it, but this had a wealth of information available. The design, avoid excessive areas of high-low pressure, and then therefore you mitigate the seltzer effect via design in the first place. So coatings, if possible, coatings can prevent the direct contact between the product and the pipeline, but as evidenced by the internal nature of this type of corrosion, it's hard to get a maintained coating inside the pipe. That brings us to the next form of corrosion that I'm going to cover, and that is chlorine corrosion. The chloride ion, Cl-, is primarily responsible for the corrosion associated with chlorine. The ion is created when Cl gains an electron or is dissolved in water. This particular type of corrosion is different to CO2 corrosion in that it can be volatile to metals in the air. It does not necessarily have to be dissolved in water. The passivating layer that, this is typical environments of chlorine corrosion. Stainless steel, the passivating layer that stainless steel develops makes it ideal for most environments. However, chloride ions can break this layer down rather easily. Drinking water. The pipes used for the transportation of drinking water are often subject to risk of corrosion via chlorine, and that's because there's chlorine in the water in the first place. So you'd find that in plumbing. Chlorine susceptible materials. continued, the reinforcing steel rebar used in concrete structures are particularly vulnerable to attack. That black Bible that we have, we spent, I think, 2 chapters covering the effect of the buildup of the scale on rebar inside concrete and how it would eventually force the structure apart, leading to huge scaling cracking. So I'm sure you've all seen old parking complexes, everything where there's a joint where there would be roofing laid across. There's typically huge chunks of it just falling out because it's very poorly maintained often, and the corrosion product has just flaked the concrete away from the structure. Any steel in contact with chlorides is susceptible to chloride corrosion, as you said previously. Possible vulnerabilities, all bridges, because they use steel rebar inside the concrete, and then the chloride attack on that concrete, well, on the metal via the porosity of the concrete, will destroy the bridges, as you said. Anything really, including buildings of any nature. There's a couple examples of what it looks like when it's encountered. This one's kind of not that great because you can see that there's the copper filament, or maybe it's brass, I'm not sure, but you can see it's green. That's not the corrosion, it's the actual faceplate. This one is from an internal kind of rupture of the pipe. The affecting factors, temperature. I just went ahead and put all these in one. As previously, temperature holds a positive correlation with corrosion rate as well as velocity and pressure. So again, if there's going to be chlorine inside of this liquid that you're transporting, you're going to want to keep it as cool and as slow and just be gentle. And as mentioned before, design has a lot to do with this too, because you're not going to have as, like Andrew mentioned previously, you're not going to have as intense corrosion on a lateral facing, just straight piece of pipe as in that first picture, as you would have in a U-bend pipe, like he was saying, because the velocity is going to strike a certain area of that pipe at a higher rate than it will the other sides. So that will experience localized corrosion attack of just a completely different thing than to do with the chlorine. That's just the act of erosion corrosion. The corrosion cell mechanism in the following example with chlorine, the chloride ion, NaC, no, it's not that. Sorry, the chloride, it's not chloride. NaCl is shown corroding a submerged section of stainless steel by creating an anodic area on the steel. There will be a picture. Additionally, chlorides promote stress corrosion cracking, otherwise known as chloride-induced SCC. This is an example of how chlorine and stainless steel can create a localized corrosion cell when exposed to oxygen in the air. Typically, the passivating layer formed on stainless steel would protect it from the oxygen, but due to the presence of the chlorine, there is just enough electron play going on, just for shorthand to say, that it can form